Hello and welcome to this homework help video. Here I'm going to talk about using Faraday's law for a magnetic field that varies in two dimensions, x and y, and varies over time in a non-constant way. Then, in the second part of this video, we're going to talk about a similar problem under the category of motional EMF, which involves a moving conducting rod in a magnetic field that's carrying a current, all right? Or at least it has an induced current in it. But let's start with this problem right here, talking about the figure, which we can see involves a rectangular current carrying loop, or at least a wire, a conductor, that a current can be induced in when the magnetic field changes, okay? How is the magnetic field going to change? It's going to change based on this time function right here. And then the magnetic field itself, besides being non-constant in time, is also non-uniform in x and y, so non-uniform in space. The loop of wire, the entire loop of wire has a resistance of 95 ohms, so that's information that we're going to need. And we need the dimensions of the wire as well, because those are going to be our limits of integration, where we actually calculate the total magnetic flux. Okay? All right, so let's then set this up. So working here with Faraday's law, we want to express that the induced EMF, all right, yep, which is, it asks for current, but of course we can relate that to EMF once we use Ohm's law at the end, is going to be equal to our change in flux over our change in time, okay? So to get our magnetic flux equation, then what we need is we need to integrate the field over that entire area. So we should have an integral for the, basically it's going to be our area integral. So in the broad sense, it's just going to be the dot product between the magnetic field and all the area elements, because the area elements are vectors that point in the normal direction. So it's just B dot dA. I'm going to confirm that that's the same one I was showing before. Yep, all inside of a general integral. Yep. Okay. Unlike any other previous examples from this particular handout, this problem here involves taking this general area integral and turning it into a solvable double integral, because the magnetic field is non-uniform in both x and y. Double integrals are just two integrals multiplied by each other, so it's simply multiplication between them, and you just deal with each integral one at a time, and then just bring together algebraically the results. Okay, so what that would look like in this problem, in terms of the setup of that double integral, would be to turn our general area integral into two integrals. One is going to go from x initial to x final, and the other is going to go from y initial to y final. Then we would, of course, put the function, all right, for the magnetic field directly inside of both integrals. And then our differential at the end is going to be both dy and dx. Okay, so when we look at this integral, since there's no case where x and y are they're all separable in a sense, where we can just then think of the double integral as just, as I said, two side-by-side single integrals. All right, almost done. So as you can see, you can solve each of those one at a time, and then that's going to be your total magnetic flux. Okay, and yep, and the units there are just going to be Tesla meters squared. If it's of any note to you that I wasn't very specific about the coefficients, but they have whatever units they need to be for this overall function to have Teslas, of course. And so the flux will be Teslas times area, or Tesla meters squared. You can interpret obviously how to do your limits of x initial and x final based on the information you were given about the width and the height of the rectangular loop of wire. And from there, then you will then take this result that you found through integration and then plug it in. At this point, it's only going to be a function of time, all right, because there's going to be no more variables of x and y left. And then you're just going to take its derivative, that final function of time, with respect to time. And the negative of that, which is just relates to Lenz's law, is going to give you your induced EMF, which you'll use Ohm's law to get your induced current. Okay? So hopefully that all makes sense, and that the last step, by the way, involving the derivative, is the same as it is in the example that was solved in class. Okay, so, and a different video for that matter. There is a video for that one as well. Okay, so looking at part B, I do want to give some hints on this. Because it is different than the in-class example. And it says, what is the net change in the current between the moment it changes, that typo doesn't help, direction, and the moment that the magnetic field is zero. Okay, so we have two moments here that you want to find a time for, and then we're going to find the delta t between them. So delta t, okay, between the time when the current or the net change in the current changes. Let me read that more carefully. What is the net change in the current between the moment it changes direction? There's the first one. Changes direction. So that is the t that we want. All right. Change direction. All right. And the moment that the magnetic field is zero. T0. Okay, so thinking about that, we've got different functions of time for both of these. Okay, in other words, for the magnetic field, it is a function of time. Okay, it's some flux times the time part of it. So what I mean by that is when you do the integral and you have turned both of these into constants by integrating them from 0 to h and 0 to w, well, what you're going to have then is just a number here, all right? And so it's just going to be some leading number, which would be this coefficient on the time part, okay? So we could say that it's like b naught, the part that is we found through integration, times the time function part of it, which would just be our 11t minus 4t squared, and then plus 19. Okay, so you can then find the zero of that pretty easily. All right, so we can then, through the fact that it is a parabola, we can obviously find out when that function achieves a zero value. That's the moment that the magnetic field is zero. That's the second time. It does happen later than the other time we were asked for. I just started talking about it because it seemed conceptually more straightforward. So then we just solve, right, for b equals 0. And of course, we'd be solving t for that. And that's your t0 value I mentioned above. Now, the other one involves the current changing direction, okay? So what's that, right? Well, what's the current's relationship to the magnetic field? It's the derivative, okay? So that means since the magnetic field, it has a second order polynomial dependence on time, the current will have a linear dependence on time. So we know that the current as a function of time is going to be proportional to t. Okay, it's some linear function, which you'll find by taking the derivative, and then all I want is the moment that the current changes direction. So when it goes from positive to negative, okay? Well, how would you find that? How would you find where a linear function, crosses the horizontal axis? you of course would set y equal to 0, all right? And y here is the function, right? So you're again solving for 0, all right? Because when I changes from forward to backwards or clockwise to counterclockwise, it must pass through 0 amps through that value. So again, we need to solve for I equals 0. Okay? Those are your two times, right? There's the calculus idea, of course, is the fact that we have a derivative relationship between the magnetic field and the current. One is the derivative of the other, and so there's a close relationship between their zeros and their maximums and so on. But in this case, I asked about both of their zeros. Okay, so hopefully that makes sense as well. Let's move on to talk about the motional EMF homework problem. Because again, there are some things that are potentially subtle and are different than the in-class example. All right, so we've got a rectangular loop. All right, it has a known length, so you're given that value right over here. Right, that is your length. Then it has a mass. That's important because we're going to deal with accelerations, and we need to know its inertia. Okay, there is a magnetic field. It is uniform, okay, and it's also constant, so very different from our previous one. Okay, but still, there are some interesting non-constant, non-linear things going on, of course. All right, that field is directed perpendicular to the plane of the loop, as shown. We can see it's actually going into the page. So the side wire is given an initial speed. Okay, so it does have an initial speed. There's no friction, all right? And there's no effect of gravity because the loop is level. So the resistance of the loop is negligible compared to the resistance of the slide wire. So that allows the resistance to remain constant, because otherwise, if we included the resistance of the wire, as more and more wire was exposed by the sliding rail or sliding wire, well, the resistance would have to go up, right? But we don't want that extra time dependence, so we have a constant resistance. How fast will the slide wire be moving after it has been in motion for 8 seconds? Okay. So thinking about this system, what's going to happen here, right? If the wire has an initial velocity, right? What's the what will the magnetic field do to it, right? Well, it's going to slow it down, all right? So what we'll see then is that we're going to have it slowed down by the field, and you can get hints of that if you look at part B, because we have how far will the side wire have traveled by the time its velocity is 10 meters per second, much slower than what it started at 104. And what is the maximum distance that the slide wire will have traveled by the time it comes to rest? Okay, because what's happening here is the magnetic field, which is creating a force that's dependent on velocity, is causing an exponential decay of the motion of the eventual the location, the final location of this object. Okay, so it will eventually come down to a velocity of 0. It will reach some maximum distance. Okay, so what does this all look like? Well, to give some context, I'll compare it to the previous example, the in-class example, because in this one, we had different starting parameters. We had an initial current, so we were told that we had a constant current being outputted, and then in the second part, more interestingly, we had a constant EMF, which created a current that didn't remain constant, because then the induced current made the overall current change over time. Okay, right. So with the constant current, it's constant. It can't change. It's almost like it's compensating for the induced current, because the total current is just always that value. You can't have a different total current. But in the case of the constant EMF, then all that's holding is the external current constant, but that doesn't mean that there can't be a different total current, because now you have the external current being opposed by the induced current, creating a non-constant effect. And in that case, interestingly, it led to come to a point where there was a balancing. So in other words, the velocity never decayed to 0. The velocity instead exponentially approached a final value, a terminal velocity. There was a horizontal asymptote of velocity. So same math, same exponentials, because those are always going to come out of the type of integral that we're doing, which is a 1 over x integral, which gives us a function of the natural log of x. But we can do different things with exponentials, right? And in this case, the exponential is approaching that final value, because there's effectively two forces. There were two forces in this in-class example: the force caused by the external EMF and the force caused by the magnetic field and its induced current. Okay, its effect on its own induced current. So those two forces opposed each other until they balanced. Okay, because one of them, the magnetic force, was dependent on velocity, the very thing that was changing. So there you go. You got this final state that's balanced out. It reaches an equilibrium. What's different here is that the equilibrium it reaches is zero. We're going to lose our velocity completely. It's where it will just slow down, because there is only one force in this system. And if you only have one force, you can't reach equilibrium, even if the force is velocity dependent. Okay, so I do want to then quickly make sure since that's kind of the big high-minded idea. I want to show the direction of the force at least, so we can really see that this is just a slowing down system. You would do this with the right-hand rule. So what we want to first of all determine is the direction of the induced current. So I'm going to use my thumb for velocity. I'm going to use my index finger to point in the direction of the magnetic field, which would be into the screen. And then that's going to point my palm as well as my middle finger in the direction of the induced current, which we can see then would be going up the page, from the top of the page to the bottom of the page. Okay, so we know that the induced current is going in this direction, just like this. So this is I induced. Okay, there's no other current, by the way, since there's no external current. There's just I induced. All right. The only thing that's external is the initial kinetic energy, or the initial velocity of the slide wire. Now let's do another right-hand rule to determine the direction of the force acting on this wire. So we did one right-hand rule to find the direction of the induced current. Now we're going to find the direction of the force from the magnetic field on that induced current. So I'm going to use my thumb for the induced current. I'm going to use, again, my index finger for the magnetic field, which is going to point into the page again. That's going to cause my palm as well as my middle finger to point in the direction of the induced force, which is not what I've called before. It's just the force on the induced current. So that's just going to show the one and only force. Okay, it's a magnetic force, and it would just be like this. Okay, so that force is going to create a negative acceleration. I would call it negative acceleration because it's opposing the direction of motion, the initial direction of motion. And we can set up a coordinate, say that's the x direction, to really square it away that it's moving in the positive direction, but it's going to be experiencing a negative acceleration from the moment the system starts at t equals 0, and it's just going to be slowing down the whole time. Okay, so in that regard, it's a simpler function. It's a simpler relationship because there's only one force instead of two. There's no approaching a final velocity because there is, but that final velocity is 0. So certainly that makes sense. What makes this, or I think that makes sense for the argument that it's an easier system than the in-class example. What does make this tricky is that I also asked for distance, which I hadn't before. Distance is found with going back to the definition of motion and taking as an integral again. What do I mean by that? Okay, well, let's set that up real fast, or get to that point by talking about the previous parts of the problem briefly. Part A, how fast will the slide wire be moving? Okay, so that's going to be the velocity one. So with velocity, we would go to the definition of it. So velocity is just going to be our change in acceleration, or rather, acceleration is our change in velocity over our change in time. Okay, so the acceleration in this case is just going to be f over m. All right, specifically negative f over m because of the direction. So we have negative f over m. We can find that F value. That's familiar. That's the same way you'd find the force in any other motional EMF problem. So I will leave that up to you. All right, and then there's going to be some L's in there. Obviously, there's going to be L squared and the B squared. I'll tell you that much. But on the other side, what do we do with the dV dt? For now, nothing. Okay. I realized that to make my point, I probably will show you the at least I will show you the form of the magnetic field function. I can't leave it up to you because I need to show that it has a V in it, so I might as well write it out. But we're going to go ahead and move the dt to one side, leave the dv on the other side because we're going to split up that differential or that derivative, turn it into two differentials. That's going to obviously bring the FB down underneath. All right. So this is, as I talked about in the in-class example, this is an interesting solution, or the approach to doing this, because there really is a best way to do it, where you're much less likely to make a mistake, because there really is a potentially tricky step dealing with the antiderivative and correctly dealing with that antiderivative and expressing it correctly. But there's ways to make it significantly less tricky, and so where it's more obvious what the solution is. So it's one of those cases where that simplifying in one way, at least as far as I know in this case, really makes a difference. It really lends some credence, right, to like in a math class where they tell you simplifying is important. It sometimes is. Okay, so I do want to show you the form of the force, the magnetic force. So that's going to be L squared B squared, yep, over R is the actual value of the force. If you wonder what I'm referring to, it would be right over here. So that right there is the force expression. All right. I'm thinking, yeah, well, and that one was the induced EMF. It just happens to be the same. So I'll write it out for us. Okay. So we have that the current is BVL. Okay. And then we have that the force, the magnetic force, is going to be ILB. So ILB. So we can substitute in for the I for the force, and the magnetic force would then just become BVL LB. Okay. And then we combine everything, and it's B squared L squared V. Okay. So that's the real application of electromagnetic, well-known formulas. This is how it fits into the calculus. So then we're going to bring that up and plug it in for our function over back there. Sorry for that. So getting back to it, we then want to have our 1 over m dt. All right, and then dv b squared L squared V. So the great thing here, although just a minute ago I was going on about how it's so important to simplify this, is that this one actually is much easier to deal with. Right now, you may or may not recognize that we got to a point where we're going to do our integration, and we're really going to be in good shape. It's going to be a very simple integral to deal with. We're going to integrate both sides because, like general rules in math, if we do one thing to one side of the equation, we got to do the same thing to the other side, so we'll integrate both sides. But what's great is, if you'll just take a quick look and humor me, if you look back here at the in-class example with the constant EMF, look what we had to integrate on the velocity side, on the dV side. There was a V minus something because of the two forces. But when there's just a single force, just the decay, just the fact that it's decaying down to rest, look what we don't have to worry about. Our dV over V is just going to be a 1 over V function. So I'll show you at least that we can pull the 1 out of m, the 1 over m out of the integral that I'm going to write on the left hand side, since it's a constant, and that integral is 0 to t dt. That's just going to give you the variable t. The whole reason we do the integral is just to say, okay, well, this is t at any point along the way, and it's just going to become our variable. On the other side, we'll have a 1 over b squared over L squared, again, coming out because they're constants. And all that's going to be left inside the integral is a 1 over v, and then the differential is dv. What are going to be limits of integration here? Well, again, you're going to put in your initial velocity, so that is important. Don't put in 0 because the initial velocity was not 0. Instead, you'll put in 104. All right. But then what do you want for your upper limit of integration? Should you put 0? Because I made a big deal in saying it's going to eventually go to 0. Well, no, not unless you want to find the time for it to go to 0, or only that would be setting it up as a definite integral for the purpose of that solution. But I would say what's better instead is to use this integral right here to give yourself a function that you can use for different parts of the question, which you will. All right. So what I mean by that is you want your upper limit to actually be v, the variable v, because once then you solve this definite integral, mind you, but still with a variable as a limit, then you're going to have v as a function of t. Okay, that's what this will give you. Okay, no trickiness here on solving it. Since it's just 1 over v or 1 over x, it's just going to become the natural log of x. Make sure to evaluate it at both limits because it matters. Okay. Whereas on the left-hand side, obviously z evaluating t at the lower limit is just 0, so that's why it just becomes t. So I won't say any more about that. You can see then that this once you have this set up, velocity as a function of time, I think that will let you answer both parts A and B, if I remember correctly, because we say how fast will the slide already be moving after 8 seconds. Easy enough. You'll just be able to plug in t equals 8. And then how far will it travel by the time its velocity is 10? Well, I bet you know how to do that, right? Plug in v instead of t and then solve for t, all right? C is the only part that's different, so I want to wrap up this video by mentioning what is going on with C, okay? The idea here was that since the function and the system was much simpler than the in-class example, I decided to make it complicated again by asking you for something that I hadn't shown you, which is how to find displacement for one of these systems, okay? Time-dependent displacement, because like in the previous one, we eventually, we noticed that we had this exponential behavior with the velocity approaching some final velocity. Well, what would the time-dependent displacement look like? Well, displacement actually, if we were to look at it for this system, it would approach linearity. If you have a very good memory, and you took a class with me before, you might remember that this is how we talk about terminal velocity, like a parachuter. So when you look at what the function looks like is it's going to be a parabola that then approaches something linear. So at some point, we'll make that the magic point, it stops being a curve, and then it's just a straight line after that point. Because the straight line would correspond to when, that straight diagonal line would correspond to when the velocity becomes a straight horizontal line, okay? So that's the idea. That's what that would look like. It's got some exponentials in it. It also has a constant in it. So it's a function that has like an x and an e to the x, negative x in particular in it. Definitely tricky to get there, right? With especially following the correct steps with your integrals. But this one, the homework problem, is not so tricky because think about what we'll end up with. Okay, we're going to have once we solve this integral, and I want to keep it somewhat vague, so bear with me here. We'd have some t on some side plus the appropriate functions like b's, l's, and m's. Okay, but we'd have t on one side, and on the other side we're going to have the natural log of v. Okay, so in particular, you'll definitely have more than one, right? Because you're going to have the natural log of v minus the natural log of something else, right? So natural log of v naught. So then that's going to become t equals the natural log of v over v naught when we use our laws of logs. And then furthermore, it'll become, and importantly, you will have a negative here as well. So you're going to end up with because there was a negative to begin with, and I wasn't concerned about it because I wanted to show other parts of this problem. But here, notice there was the negative. I didn't write it, or I wrote it in this step, but then I never brought it back over here. So that's important because actually it would be over here, and it would be over here, so it'd be negative t. Why does that matter? Because you need that negative exponential, and it will be there naturally. So then it would just be negative e to the t. That's your time-dependent decaying exponential. And then that's just then going to be your v over v naught. So, and really, besides some constants, this is what your answer to part A will look like. So that just gives you then that your v function is the initial velocity multiplied by e to the negative t with the appropriate constants up there in the x. They'll be up there sharing space with the t, of course. Okay, so that's the idea, right? If you plug in t equals 0, then this just becomes 1, right? And then that tells you if that time equals 0, v equals v naught, as it is, right? And of course, it's decaying down to 0. I mentioned it a few times, but I'll add in the shape here, even though this is all in service to telling you what's going on with the displacement. So this is x, this is, sorry, it's still v, it will soon be x, and here's t, and so here's v naught. So the actual function is it just decays down like so. That's the velocity decaying down to 0. Okay, shown by something that looks like just like this with the appropriate constants. All right, but then what do you do for the next step, right? This is interesting. All you do is take this function and rewrite it so that this right here, this v, becomes the definition, which is dx over dt. Okay, the derivative definition of velocity. Okay, and then on the other side, you're still going to have your v naught e to the negative t. You will again separate your derivative. All right, so we would again separate things, and in doing so, we'll just set up another integral, and not a terribly difficult one to solve. We're going to have the dx on one side, and then we will have the v naught e to the negative t dt on the other side. Okay, so that's after we've separated the two of them. Okay, it makes sense to have the t dt, that is, on the same side as a function of time. Yeah, you're obviously going to deal with that accordingly, and you're going to set up your integrals in a very similar way as what I was talking about above when I was talking about going from the definition of acceleration, okay, which is of course what we did right here, right, just as we've done here with the definition of velocity. But when you did all that, right, you got to a point where you then integrated from 0 to t, and then from v naught to v. Well, here you do the same sort of thing on the side that just has the dx, and there of course you'll have more constants. You would go from 0 to x dx, and on the other side you could pull out your constant v naught in front, right? It truly is just a constant, not a function of anything. It's 104, right? And then you'll have some limits here, which I'll mention in just a moment. Your e to the negative t, being a function of time, stays inside the integral, and of course then there's a differential dt. What would be your limits, right? Well, what are you trying to find out here, right? Well, this needs to be 0 to t, okay? So it's interesting, right? Because before the 0 to t was on the side where not much was going on. Now the dx is, okay? Because we have velocity entirely as a function of time. However, when you solve this, what you'll find is you will find that this function, especially with the correct limits, all right, because you're going to go from 0 to x, and you're going to solve for the final location. I want to make sure I'm not misleading you, because when I see this, it doesn't look like, okay, oh, no, it'll work because the e to the negative t will give you the 1 that you need. Because this is another case where you can't just write off the lower limit and say, oh, it's 0, it just becomes 0. Because of course, e to the negative 0 is not 0, it's 1. So when you evaluate that lower limit, what that's going to give you this essentially asymptotic behavior, you will find that the displacement over time approaches some final value. What that means is that, since the slide wire is slowing down and slowing down and slowing down, and its velocity eventually becomes 0, that means eventually comes the rest, and wherever that happens, right, that's its final location, its resting location. Now everything approaches but never quite reaches it, because it's all a matter of exponentials and logarithms. But this would be your x and over time, and so your initial x is 0, right? You start at the origin, but then you're going to approach that final value. Okay, that final value of x final, and that is what I ask for. That's what you're going to be answering with. The maximum distance is just the final location, x final. Okay, all right, so hopefully that all makes sense. And by the way, that's literally what this could be. You can think of it as a variable, right? Because then it could be a variable t. But if you're just going to find the final value, then you can do it that way. Okay. And there might be some, you might find yourself thinking about like, well, what value of t do I put in there? So, well, you can think about that, right? What's the biggest value of t and what's the consequence of it? So hopefully that will guide you on how to make sense of it. But you are just going to get a number. You're going to get a final value of how many meters the wire travels. I believe it's actually a very large number. Okay, well, there you go. Homework help for the 2 homework problems from this week's handout. I hope this didn't run too long. I hope it's been helpful. Thank you so much for watching.